This video is a short introduction to metal-oxide-semiconductor field effect transistors, MOSFETs, often just called FETs. It corresponds to the first part of Chapter 32 in the book Applied Analog Electronics. Now, let's start by drawing a symbol for a field effect transistor. The basic symbol has two terminals for the source and the drain, and another terminal for the gate. And the pair of parallel lines here, which is sort of reminiscent of a capacitor, is deliberate because there is an oxide that's generally silicon dioxide, sometimes a little bit of silicon nitride as well, insulator layer there between two conductors. One conductor, traditionally metal, but often now polycrystalline silicon, is the gate electrode, and the other conductor on this side is the channel that connects the drain and the source, so that we have effectively a capacitor. All right, there are several different types of field effect transistors. We'll deal in this class with the junction field effect transistor, which we saw briefly for the microphone, and with two types of MOSFETs, N-channel and P-channel, which has to do with what sort of charge carriers are in this semiconductor region, the channel, that conducts between the drain and the source. We'll deal only with enhancement mode ones, which are basically turned off by default and get turned on by voltages on the gate. And the enhancement modes is shown by doing sort of a dashed line here behind the channel, and then connecting the middle of that dashed line to the source with an arrow. The direction of the arrow tells you whether it's an N FET or a P FET. Basically, N points in. So this is an N FET that I've drawn. And the source is where the charge carriers come from. So we would have, because this is an N FET, the charge carriers are electrons, we would have electrons moving from the source to the drain, which means conventional current flow, which is the opposite of electron flow, would be in this direction for an N FET. For a P FET, the charge carriers would be holes, positively charged, and so the conventional current flow goes from the source to the drain in P FETs. Let's just look at N FETs for now. Okay, what are the characteristics of an N FET? What does it look like? How does it behave? And there's sort of a generic way of drawing the behavior of a three-terminal device like this. And that is, we look at what is the voltage from the drain to the source, and what is the current through the drain. And because the gate is electrically isolated by that insulator layer between the semiconductor and the metal or polycrystalline silicon of the gate, the current through the drain is the same thing as the current going from the drain to the source. All the current that goes through the drain goes through the source also. Okay, so this current versus voltage plot is a pretty standard way to represent semiconductor devices, three-terminal ones. And what do we get? Well, at very low voltages, the current goes up kind of in a straight line. And then as we get to higher voltages, it rounds off and eventually becomes pretty much constant. This constant current up here is called the saturation current. And we generally talk about sort of two regions of behavior. The linear region, where the current goes up linearly with the voltage, and the saturation region. And both regions have some use in designing with field effect transistors. Since we're going to be using the field effect transistors mainly as power transistors putting a large current through them, we don't really want to be in the saturation region, because in that region, if you look at how much power is dissipated in this device, well, we're not getting any more current as we increase the voltage. So we're going to be dissipating more and more power through the device without really controlling anymore. So we're generally going to be working down in the linear region where the current goes up linearly with the voltage. Well, current linear with voltage, that can be modeled as a resistor. So we can think of this thing as a resistor. Well, if we just wanted a resistor, why didn't we just use a resistor? This is where the gate comes in. The gate changes this characteristic. What I've shown here is sort of a typical characteristic for a transistor that's turned on. That is to say that the gate voltage, or more specifically, the gate to source voltage between the gate and the source, if that's high, then we get a characteristic like the one we've shown here. If it is very low, we get a different characteristic, one that looks more like constant zero. Like our connection, instead of being a resistor, is an open circuit. So we can use this thing now as essentially a switch. With a very low gate voltage, we've got an open circuit. With a very high gate voltage, we've got a resistor. Hopefully not a very large resistor. And the important things are for this is, well, how much current can we put through it? Where does it saturate? That tells us, hey, we're getting out of the linear region. We can't use this transistor the way we want to. And how much resistance do we have, which is kind of the inverse of the slope of this line. So we want to have very large current with very low voltage. So we would want a very steep line, very low resistance. All right. We can look at data sheets to get these curves, but sometimes it's nice to try and measure our own. Unfortunately, with the power field effect transistors that we'll be using in this class, it's hard to measure your own because the resistances here are very tiny, and the test setups and stuff we can build with a breadboard and stuff have much larger resistances than the things we're trying to measure. So it gets very difficult to do this setup unless you have very high currents, which we can't get with our equipment, and very, very low resistances for the measurements devices, which is also difficult for us to do. However, if we use a non-power field effect transistor, so I'm going to say, let's look at what would happen if we used 2N7000 field effect transistor. That's not the sort we use in class. It's got a pretty high resistance, but that means it's easier for us to measure. All right, so what I did is I have another sheet of paper here to show you the test setup that I made. I took one of these transistors, an NFET, put one end to ground, and I put a load resistor here of 150 ohms, and I connected it up to a voltage source. And then I put a gate voltage here that I could control with the analog discovery 2. So now I can look at what's the voltage across the field effect transistor. I can look at VDS, and I can look at what's the voltage across this resistor. So I can look at ID. And I can change the gate voltage to say, well, how does the gate voltage change the resistance? And I'm not going to do that live for you. I'll just show you the results. All right, when we've got a low, let's start at the high end actually. We've got a high gate voltage. So the gate to source voltage is 5 volts here. Then the resistance is on the order of 3 or 4 ohms here. And it doesn't change much with the gate voltage. Basically, the transistor is as on as it's going to get. Once we get below about 2.5 volts, then the resistance gets much larger. This is the region where we get into what's called sub-threshold conduction, where we're below the point where we think of the transistor as being on. There's still some current getting through, and you can see that the resistance goes up exponentially. And here I mean that exponentially in the literal sense. There's a logarithmic plot there for resistance, and we're seeing a nice straight line as the voltage drops that goes up. The resistance goes up exponentially. So the threshold voltage for a field effect transistor is basically at that corner there, right where we make the transition between this sub-threshold exponential behavior and the basically constant on resistance. That's the threshold voltage. And that's usually reported on the data sheet, is where do you make that change in behavior. Now, the 2.25 volts here that we're seeing for this field effect transistor is not unusual. But the field effect transistors that we'll be using for controlling the loudspeakers, for the power amplifier, usually are selected to have fairly low threshold voltages, because we're going to be operating this whole thing at a pretty low voltage. And so it's nice to be able to turn the transistors on without needing to put a high voltage on the gate. And a lot of field effect transistors these days, because they're designed to operate with digital logic that's running at lower and lower voltages every decade, now often have quite low thresholds. If you get one of the older power transistors, they may have even a 5-volt threshold. So be very careful when you are selecting a transistor not to look just at what is the on resistance, which is this region here where the transistor is basically fully on, but where do you make that transition? What is the threshold voltage? Okay, so I've explained the threshold voltage. I've explained how to think of the transistor as a resistor. There's one other little thing we can look at, something that we don't actually use, and that is when you're in the saturation region, how should you model the transistor? Basically, in the saturation region, if you model it that way, you end up with a current source. And how much current you get, again, depends on the gate voltage. And most of the data sheets are actually very good at giving you this information, because the plots that we have often have not just one curve like I've shown here, but they often show multiple ones labeled by different gate voltages. So you can easily read the saturation current off of just where is this horizontal line for different gate voltages. And that'll give you an idea of sort of where it is that you have to say, hey, I want to put 10 amps through this thing. Well, with the gate voltage I'm using, I can only get 2 amps through and hit saturation. This is not the right transistor for me. So saturation voltages are also very important to look at, and those are usually read off of a curve like this one, because it depends very much on what gate to source voltage you're using to control the transistor. Okay, I think that's enough for this introduction. We'll have several other videos that talk about different aspects of field effect transistors.